I'm starting the live stream. Welcome back, this is Dual Maths. I'm James and I'm learning about quadratic residues, quadratic forms, that sort of thing. Bit of a sudden start. I think I've jumped the gun on 4 o'clock. Hooray! Right, bonus content. What are we going to do for the bonus content before 4 o'clock? I don't know. Let's look at some quadratic residues together. iTwitch, hope you're doing all right. Right, we've got a calculation that we looked at a couple of weeks ago to work out whether 78 is a square number in the mod 89 universe. And the answer is yes. Although this method does not tell us what squares to 78 mod 89, so that might be a fun side question. Maybe we could list out numbers. Hello in chat, Mary and Maths22222 who have joined. I updated the t-shirt command because I didn't want it to become my uniform, so I'm not wearing the Gaussian Primes t-shirt today, but Maths222 says that they are, so that's nice. There you go. Someone else out there owns the same t-shirt as me. I don't know why that tickles me so much, but it's been true before. Yeah, not in uniform. It almost became a uniform, right? I wore it twice in a row. That's almost enough to set a sequence going. Twitch says live but unstable. That's a nice message to read. It doesn't give me any tips of what to do about that. My stream bitrate is too high. It gives me one tip. I've forgotten what those words mean because it's been a few years since I set up Twitch, but maybe I'll turn that down if I remember. Let's write a note while I'm here. Hey, if you join at 4 o'clock on the dot, you get kind of stream admin, where I'm trying to work out what on earth I'm doing. Stream bitrate. All right, it's too high. Oh wait, no, that's not quite the message. It says average. Interesting. Right. We'll investigate that another day. Right, okay, so if you've watched the show before, we are learning about the values that a quadratic form might take. Our favourite one is x squared plus y squared, but we've also got a lot of time for x squared minus 2y squared. These are quadratic forms where you have terms like x squared, y squared, or xy with integer coefficients, those three terms, 0 on the middle term in both cases here, and you're interested perhaps in what values those can take. We've seen a fact that x squared plus y squared equals n. So if a quadratic form, let's do a general statement. If a quadratic form x squared plus bxy plus cy squared takes the value n, if and only if, and then the rule is that the discriminant has to be is a quadratic residue. So this means that it's sort of like it's a square number in the modulo world, modulo 4n. So if you care about a fixed number, then you're working in a fixed mod world. Otherwise, there you go. We've been quite interested before. Have I got that the right way around? I think I've got that the right way around. Is minus 4 a square number mod 4p is a thing we've been asking about. Yeah. Which is the same thing as saying is minus 1 a square number mod p, which has been quite fun. Maths222 has been reading about this in linear algebra as well. There you go. Quadratic forms are handy. Oh, you can use elementary linear algebra stuff to diagonalize a quadratic form. I think I think that uses real numbers, or maybe even complex numbers though, because I think you probably want something about eigenvalues existing, which is not a route available to us as far as I know, if we're only interested in whole numbers. But you're right, we can diagonalize. Right, okay, sorry about the noise. I've made a compromise solution. Last week we tried fully windows closed, which raised the temperature in here by about 5 or 6 degrees, and we tried fully windows open, which was extraordinarily loud. We're on a compromise today. Loud and hot. Right. There's the tagline for the show. Chill Maths, loud and hot. Right, the weather today is changeable. We've had a lot of rain, we've had a lot of sun. It is called British summer, I think. Right, okay. We're going down here. We're going to get in, I think, down here. I think have I got a bookmark somewhere? No, but we're going to go again. Okay. So this form obviously represents 2 because 1 plus 1 is 2. And then there's this question about primes that I just try to remember out loud. Yeah, and we have the second property, which we've now seen a proof of, I think. somewhere out there we read onwards quite a lot, and in section 6.4 or something we saw proof of that fact. Here's a quadratic one we care about as well, with discriminant 8. Discriminant is b squared minus 4ac. B is 0 minus 4ac. It really is 8. Good. The only prime dividing that is 2, which is represented like this. For odd primes, so we have to worry about cases where it shares a prime factor is a bit different. Hello, Mean Machine Rex. How are you doing? Hope you are. Well, I've gone back about 30-40 pages from last week's heady heights of learning why quadratic reciprocity is true, all the way back down to actually what do you do with these things, why are they relevant? And there's a single fact that we've got that makes them relevant, to do with representations, things that they can represent. Sorry, not to be confused with the mathematics of representation theory. Right, okay. X squared plus 2y squared can take different primes. Primes represented by this one are 2, and the ones that are 1 or 3 mod 8. And this one can take the primes 2 or 1 or 7 mod 8. So that's kind of fun. That minus sign makes a big difference. And that's one that we maybe care about if we're looking for Eisenstein triples using integers, I think. Can't remember what an Eisenstein triple is. Maybe I'm talking absolute nonsense. You know, triangles with a 60-degree angle or maybe a 120-degree angle maybe have a version of Pythagoras that's a bit like this. So if we're looking for triples like that, maybe we care about this. Which primes can you see in there? And then big case. Let's read this again. So yeah, okay. So is 40 a square mod p? You can break these things down into the prime factorizations of the number upstairs, and then this is always 1 or minus 1, so you can ignore the cube. I remember this from a couple of weeks ago. Okay. And oh gosh, you get this weird collection of cases. What a mess. Okay. In these cases, we could do it like this. And this is enough. So a couple of weeks ago, I think Maths 222 asked about having whether these facts were enough. We argued a little bit about whether you need all of them, but here we are. We're going to see something, I think. Yeah, if you put a minus sign in, okay, I'll take that then. I remembered in time that I should say, or maybe 120 degrees. So there we go. Yeah, Math, you've got Math 222. You've got a capital letter now, right? Did you always have a capital letter? Is that just a thing we can do on Twitch? You know, I've got 2, so and Mean Machine Rex has got 3, so we're handing out capital letters all over the place. Ah, you did that on purpose. Oh, there you go. Nice. Capitalise your maths. Yeah, it's somehow really noticeable. 10 minutes ago. There you go. Treat yourself. If you're on Twitch and you have a username, apparently you can just add a capital letter wherever you like. Go for it. Right. Okay. Here's proposition 6.9. We're going to learn that the facts we've seen so far are sufficient for all of our dreams. Let's go. So if you can factorise it like this, where, what is that, plus or minus 1, fine. Do I love epsilon being the name for plus or minus 1? No. Can I remember it? Fine. Some power of 2, and then some primes. These are the odd primes. That's unique, I suppose, because of prime factorisation. You're allowed k equals 0. None of these when it's a power of 2, plus or minus. Okay, fine. Yep, good. Then for odd primes not dividing the Legendre symbol, one has the, no, for odd primes not dividing delta, comma, the Legendre symbol like this has the value given in the following table. Ah, what is this? What is all this? Yeah. I kind of agree. What is all this? For odd primes not dividing delta, the Legendre symbol has the value given in the following table. So, odd primes not dividing delta, which is the ones where these are supposed to be co-prime when you write down the Legendre symbol. So good news, we're looking at prime p that doesn't divide delta. And what does this say? So this has turned them all over. Has it applied quadratic reciprocity? some crazy number of times. Oh, but we know how many times it's applied to quadratic reciprocity to get the p's upstairs. Look, what's going on here? It looks like all of them are flipped. And where isn't there a -1 to the k? Oh, because the -1 only comes if they're both 3 mod 4. The question is going to be how many terms in the prime factorization. These can be repeated, but how many terms in the prime factorization are 3 mod 4? And that's everything to do with also, is that section over there that's the product of all of those primes, is that 3 mod 4? Because, right, don't I care about whether, right, there's separate cases depending, I think, on whether P itself is 3 mod 4 or not. If it isn't 3 mod 4, then you're just allowed to do all this flipping and it's fine. But to think about the 2's separately though, and you're allowed to do all this flipping and it's fine. If it's 3 mod 4, then you'll get a minus sign every time one of these primes is 3 mod 4. But if the overall product is 1 mod 4, that must have an even number of times, so you're fine. Think about the 2's in a moment. If it's 3 mod 4, then I kind of agree that you'll get an extra minus sign. Why is that upstairs though? Something's happened. They've done an extra flip. That's fair enough, I suppose. You could bring the minus sign in at the start to turn it into something that's 1 mod 4 with a minus sign at the front. Why aren't there any epsilons in this? Oh, because M's, that includes all the cases, so you can always flip it to a case where you get the desired. There's no plus or minus signs here, that's fine. The question is whether epsilon and all of these things, it is 3 mod 4 or not. Possibly separately thinking about plus and minus signs. And look, here are some more cases. Is this just the other way around? Oh no, this is extra factors of 2. So what's going on with the 2's? So I'd expect this to be 2 over P, Legendre symbol, a certain number of times. But if it's an even number of those, then I don't care because it will factorize out an even number of times. And if it's 1 or -1, I don't care. But if it's an odd number of 2's, then you'll get 1 left over. I think that's all that's going on here. There's something tricky about how many 3's and 1's, how many 3 mod 4's and 1 mod 4's do you have in your prime factorization, which is represented here by is the product 3 mod 4 or not, and down here by how many minus signs do you get when you do quadratic reciprocity on everything. I think that's what this is saying. It's nice to try and read it before the proof's on screen, isn't it? Because when the proof's on screen, everybody just reads the proof instead of listening. Not that you're supposed to listen to me. What sort of show is this? Right, okay, proof. Here we go. Quadratic reciprocity. And not out loud. Let's see what they've got. They've got the epsilon in here. Are they going to combine it back together? Where omega is 1 or -1, according to whether there are an even or odd number of factors that are 3 mod 4. Yeah, okay. And then this exponent s can be replaced by 0 or 1, according to whether s is even or odd. That's fine. Okay, that's the thing about the 2's. So this omega thing, they're being careful to say. In the first and third rows of the table, the odd part of delta is 4n plus 1. What are we? Are we partaking? Partaking of something really good, right? We're all joining in together, right? Yeah, in my head it's a kind of committee meeting. We're gathered here today to discuss this large product of primes. Is it 1 mod 4 or is it 3 mod 4? It really depends what primes are. I'm surprised that the omega is inside the brackets because I've been thinking about this as giving me a certain number of 1's or -1's. So that's throwing me. Second, fourth row. This is replaced by 4n plus 2. What is this? Wave epsilon is minus omega. I think they are just tracking all the minus signs, and if I write it out, then it would be fine. I think it's what I said out loud. Putting the minus sign in changes things between 1 mod 4 and 3 mod 4. I have to remember that flips everything. Common trap, I think, to think that -3 and 3 might be the same mod 4, because they look the same. Mostly a 3, isn't it? But 3 and -3 are not the same mod 4. -3 is confusingly 1 mod 4. That's really annoying, isn't it? If you take out a factor of -1 of w over w word, do you mean over w there? I'll roll with it, but me WK, right? Rule 4 is the quadratic reciprocity one, and it says that it only applies to odd primes. So I can't use rule 4 with -1, so I don't think you mean 4 either. I think you mean rule 1, which rule 1 is about pulling out a factor of -1, and that's the one I'm thinking of, I think. But we only want to pull out that -1 if... Yeah, it's fine. Yeah, it's fine. You just have an extra minus sign left over sometimes. And if you manipulate the number before you start, then you can have it in here. I'm just confused because... actually, no, this is bad because the way I'm thinking, -1 over p is sort of always -1. The way I'm thinking, which is not a healthy way to think because it's not true. And that's only true if it's 1 mod 4. If p is 1 mod 4. So I think I want to write something out. I've not quite got how that W or omega or something appears upstairs inside the Legendre symbols. So I'm going to stare at this a bit more, and I'm going to think hard about what I want. So, yeah, okay. So in this case, I was thinking about this being a positive number, a product of primes that are 1 mod 4 and an even number of primes that are 3 mod 4, but it could be the case that this is describing an odd number of primes that are 3 mod 4 and a minus sign, because then it would be 4m plus 1 overall. So the negative numbers are a little bit different here, because all my primes are positive. So in that case, where I've actually got an odd number of... What am I talking about? And it hasn't split. I thought it would split. I realise now it hasn't split into cases where p is 1 or 3 mod 4. What is going on? So this is obviously true. This is rule 1, that you can split out the factors. And then spot the difference? Spot the difference here. So the primes are all flipping, and where are we getting this omega from? We're keeping the epsilon on the front. With an even number, okay, let's think about the first case. Even number of factors that are 3 mod 4, then introduce a minus sign to the number? No, because I just want to flip these positive primes. Why is the omega inside a bracket? Why is it not just a big pile of -1s, right? From the quadratic reciprocity thing, which says that you sometimes get a -1. Why is it only that if p... Oh, right, hang on. It's only that because that also depends on whether p is 1 or 3 mod 4. So this is not obvious, I think. It's not an obvious application of the rules. It's just here to track whether p was 1 or 3 mod 4. Because if p is... Right, okay. So it's just kind of... I could read this as just a kind of clever mechanism. That's just a kind of case thing, which I think just says, yeah, using the -1 factor, that this is just a bonus factor of plus or minus 1. Why have I regressed? I know, I feel like I've got a lot worse at maths and pages in the book. Don't look at the page number. So this is a kind of bonus factor. Yeah, I think we are allowed to say that, but then I don't know if we can use quadratic reciprocity on what you're about to use. Is maybe -pn is now a negative number, I think. I don't know if you're allowed to use quadratic reciprocity on that. I sort of suspect that we only have it for positive primes, and that for negative primes, if we're not careful, there's an extra factor there. But I'm going to read this as just a bonus factor, depending on whether P is 1 mod 4 or not. If P is 1 mod 4, nothing to worry about, because whether this is 1 or minus 1, those are both 1. And if P is 3 mod 4, then, oh, now we've got to think. And then in that case, so if P is 1 mod 4, I don't care about this term at all. It's scaring me, but I don't care about it at all. And if P is 3 mod 4, then the number of minus signs that I get out of this, well, depends on the parity. So read on to find out how this matters. But I'm going to want a minus sign here if there's an odd number. It depends on how again. So there's kind of a yes-no switch inside a yes-no switch, and that is precisely the right behaviour. Yeah, so that has the opposite parity, but I just don't know whether... I think we've only proved quadratic reciprocity for positive primes. I'm sort of only believing positive primes for this book. I know that the negative prime would have the opposite parity and it would superficially sort of fix things, but I don't know if we actually have that fact or not. Okay, I would like to understand that as a kind of bonus switch, depending on all of the terms and conditions in quadratic reciprocity, boiled down into one simple term with several if statements kind of nested together. Maybe that's not a healthy way to think of it. Maybe I should think about negative prime numbers, like Maths 2 is currently thinking about. Maybe. Oh, and I missed 3 questions from Mean Machine Rex, asking why I haven't moved on to class groups. We'll get there. Yeah, why not complex numbers? If only there were a t-shirt where we could learn more about complex prime numbers. Quick. Plug the shirt, Oh, phew. Good, almost missed an opportunity to... Right, okay. I've made a t-shirt. I'm very pleased with it. Okay. What is this then? So this is telling me about the separate cases where you could then simplify this. So we actually know about the sign of 3, how many 3s and 4s? How many 3s and 1s mod 4 there are for our primes, looking at delta itself. These cases. The odd part. Okay. I think I'm happy with this. It's sort of then recombining these terms together again. So I like this because it's thinking about the minus sign at the front totally separately. And it's only using positive primes. And okay, you've got to be a bit careful with how many negative signs you pick up through quadratic reciprocity, but you can do that with a single Legendre symbol. So I need to be a bit happier about that, I think. The omega is measuring how many times this thing has happened, and the P down here is measuring whether or not it's happened at all. You could switch off all of these if only -1 were a square number. Right, that's right. The stream now has mid-roll ads and product placement. We got everything going on for a small Twitter show. Really trying. Oh, sorry, for a working group based around maths. Really got that hustle going. Right. Okay. It's not obvious that I'm making fun of myself. I am almost always making fun of myself. Good. Okay. So 6.10. Ooh. The representability of an odd prime P in discriminant delta in general, not just -4, the one I really care about, depends only on the congruence class of P mod delta. So this is going to be because of reciprocity or something. Here we are. Right, the class of P mod delta depends... The class of P mod delta determines its class mod Pi for each I, and this determines these things that we just had in the lemma or whatever we just saw, proposition 6.9. For the terms like this, in the last 3 rows of the table, note first that L must be at least 1 in these rows. L, the power of 2, maybe? Since delta is a discriminant. Oh no, which I know is 0 or 1 mod 4. In the second row, 0 or 1 mod 4, so it's either a multiple of 4 if you're 1 mod 4. L must be at least 1. What's L? What's the power up here? For the first 2 rows, note that L must be at least 1. Is that what it says? No, in the last 3 rows of the table, note that L must be at least 1 in these rows, since delta is a discriminant. Right, that doesn't make any sense to me. This is telling me that you must have loads of factors of 2. Delta is a discriminant. So chill. There you go. Let's stay chill. What have we got here? I'm going to read on and then come back to this because what on earth is this? Which property of it being a discriminant are we alluding to here? The whole book is about discriminants, more or less. We know so many things about discriminants. Which property of discriminants are we alluding to? The fact that they have loads of factors of 2, that's just not true though. They don't have loads of factors of 2, some of them are odd. Don't know what's going on, chat. You don't know what's going on. Oh yeah, we also have a mug, how could I forget? He's on screen. Right, in the second row, the class of P mod delta determines its class mod for its me. I'm making fun of myself again. So it determines... Oh gosh. I just got completely out of my depth really, really suddenly. What is this? Class of P mod delta determines class mod 4. What is this magic? So, so then you can work out -1 over P. In the third and fourth rows, the class of P mod delta determines its class mod 8. So both these and these are determined. Oh my goodness. Thus in all cases the factors are determined by the class of P mod delta, so that's determined. Right, we're in deep trouble here, chat. What is this? In the second row, class of P mod delta determines its class mod 4. Okay, we can do this. Okay, so what are we looking at here? We've got different cases. This includes things that are odd. The odd determinants are all in these first 2 cases. And if I'm worried about odd numbers in particular, I feel like I am. Because here I want to tell you facts about how, well, if delta's even, then it's a multiple of 4. And that would be quite good because then knowing P mod delta would tell you P mod 4. You would say, like, it's 37 more than a multiple of delta, so I would go, aha, it's 37 more than a multiple of 4. Wait a minute, it's 1 more than a multiple of 4. That would be good, because knowing there's 1 more 4 lets me say more stuff afterwards. That's if it's even. If L is 1 or more in these 2 cases, then I can see how you can work out this thing. And, right, so... If you know, let's try and build it again then. P mod delta tells you P mod, right, okay, it doesn't, okay, so maybe I don't know P over P1, Legendre symbol, because how would I? But I can see that the congruence class of P modulo P1 is the only thing that matters here, and if you know the congruence class of P modulo delta, then you can tell me the congruence class of P modulo any factor. So I can see how most of these are fine. So it's just the -1s and the 2s that we've got to think about. In the first case, delta might be, or there's nothing else. In the second case, we're good in that one. I understand how you could get all of these out of information of just by telling me P mod delta. I would, in principle, be able to go and work out all of these things. So, by which I mean, for a fixed delta, primes, the congruence of P modulo delta tells you everything about how to calculate these, which tells you whether or not you can represent primes of that form. They kind of all go together. Modulo delta is the key to understanding whether primes can be written with this quadratic form or not. Which for our favourite one is 4. That's why the answer to which primes can you write as the sum of 2 squares is all about modulo 4. Okay, this seems important. I think I've got to understand it. Okay, so in this case, I've got to know whether P is 1 or 3 mod 4, and I know P mod delta. So if delta's a multiple of 4, I'm happy, because then I obviously know what P is mod 4. If delta's not a multiple of 4, then I've got, well, don't I have a problem? Because if delta is, delta is a discriminant, so it's either, right, here we go, delta's the discriminant, so this second case is kind of interesting, right? Doesn't the second case only happen? This is a fact about factorising any number, but we know that delta is either or 1 mod 4. That is the important fact, I think, which means that in these cases, right, here we go. In these cases, if you have a factor of 2, if you're even, then you must have at least 2 factors of 2. You must be a multiple of 4. And this one definitely has a factor of 2, because there it is, as an odd number of factors of 2. This one definitely has a factor of 2, so it must have lots of factors of 2. This one might not, but if it doesn't, it would be 3 mod 4. So it must be ones that are 0 mod 4. I see. Okay, so in all of these cases, L is at least 1. I've got there in the end. It is just because they're 0 or 1 mod 4. Right. Ooh. Chat's talking about onion rings. Okay. Right, in we go then. So, in this case, I know there must be some 0. I know we must have L greater than 1. It can't be left on its own, being 3 mod 4. This is how I got it in just now. I realised that delta being 3 mod 4 would be confusing, because you wouldn't be able to work out whether a prime P armed just with P mod delta. You wouldn't be able to backtrack and work out whether P was 1 or 3 mod 4. It depends what multiple of it would break down, wouldn't it? What do I mean by that? But never mind. It doesn't happen, because delta can't be 3 mod 4. I think it would be a problem if it was, but let's not explore that right now. And then in these cases, well, good news, delta is 0 mod 4, so you must know what P is mod 4, which answers this question up here. And in this one in between, you need to know what P is mod 8 in this case, but that's fine, because once you've got, in this particular case, L is at least 1, you don't just have one multiple of 2, and this is the odd case, so you have 3. The only case where you need to know what T mod P is, which is both of these actually, it's because you have so many 2s that the number is now a multiple of 8, and P mod delta is enough. Right, thank you, irregulars, there we go. Oh, the little T-Rex emoji is very good. Right. I'm catching my chat at the same time as well. Remove the star, either 0 or 1 mod 4. Note to self. That is, in a nutshell, glad we did that. That is what a lot of reading maths is like, right? You've seen it happen a few times, I think, but something is impossible to understand. But then, after lots of work, you go back and you work out what they're trying to say, and you've learned a thing, with a reminder that in this table, this is all the possible ways to factorise numbers. You could pull out some number of 2s that might be an even number or odd number of them, and then you're left over with an odd bit that might be 1 or 3 mod 4. But if you know the number overall is either a 0 or 1 mod 4, you can say better than that. Right, okay. I think I understand the first of them now. With all the minus ones. Okay. Right, okay, so this is good news. This says that we only have to think about P mod delta. Delta might be a large number, but if you want to know which primes can be written with a particular quadratic form, then you just need to work out what's true for primes of each congruence class. I don't know how you're going to do that, but, well, yes I do. You're going to go and work out all of these quadratic residues, and you're going to multiply them all together. Good luck. There's loads. Yeah, so maybe 6.9 is important as well, because it kind of gives a recipe to say, can you write this prime? And then, whoa, you're going to need lots of things. Off you go. And then hard question, do you actually need the -1 thing? kind of feel like... well, then let's not think about minus ones because I seem to find them very, very confusing in the proof of 6.9. Maybe we can get that. Which types of prime go into 4m plus 3 and how many of each? Sure, so 4m plus 3 is... well, it's minus 1 mod 4, right? So I think maybe your question is, if you just know the whole thing is 4m plus 3, which types of prime are in there? Well, if you mean, by types of prime, if you mean things that are 1 mod 4 or 3 mod 4, all multiplied together, then there must be an odd number of things that are 3 mod 4 overall. I think, is that what we're going for? So that overall, they're a bit like minus signs. We need an odd number of them so that we get 3 mod 4 overall. Cool. So that's why this summary is a little bit of a fake out in a way. They tell you that they're going to factorise this number, but then the only thing that matters in this table is not kind of how large k is or what these primes actually are. The only thing that's important is whether their product is 1 or 3 mod 4, because the only thing that's really important is, okay, their product, but equivalently, the parity of the ones that are 3 mod 4. Do you have an odd or even number of those? Which controls whether the product is 1 or minus 1 mod 4, and also controls how many minus signs you get out of this quadratic reciprocity thing. Right, good, okay. They can even be the same as each other. They don't need to be distinct, it's kind of cool. Okay, right, we're going to generalise theorem 6.8. I can't remember what theorem 6.8 was, so I'm going to scroll backwards until I find it. Oh, my goodness, was it ages ago? Let's see. Is it one of those ones where we stated it, we didn't prove it? 6.7, 6.8. If there is a fundamental discriminant, then the numbers n that are represented by at least one formula that's for exactly the numbers, page 10, that factorise a product like this of products. I think primes p. But we didn't prove this, each of which is represented by some. Okay. Oh, no, maybe this is where we talked about... we haven't proved this, but we have got, I think, but we have got quite close to proving this. We've got quite close to proving this. Where? Yeah, splitting things apart and then looking at these. No, I don't think we've done this at all, have we? Actually, I've decided. Oh no, we have, apparently, and I've forgotten all of it. Right. For fundamental discriminants, so I think I'm going to reread this, because, oh gosh, there's a lot of notes on this. So I'm regressing, I'm going backwards, but I think it's good for me. Yes. Yeah, 4n plus 2 is an even number in chat. I just expanded and eventually simplified to get the result, but 4n plus 3. 4n plus 3 is the case where you actually need to use quadratic reciprocity in the sense that you get some minus signs along the way, depending on p. In my head, that's still two separate cases, subcases, for whether p itself is 1 mod 4, in which case I don't care about the minus signs from quadratic reciprocity and everything's fine, or is it 3 mod 4? In which case, I get a minus sign every time for all of these PIs that are 3 mod 4. What on earth was going on? This was now like 3 weeks ago that we looked at this. Each prime dividing the discriminant is represented for prime divides delta, but not the conductor of delta. No. I remember struggling through this about 2 or 3 weeks ago. Oh dear. Put 4n plus 2 in the table. I guess it kind of would work because they're separate cases. There were 4 cases in that table, and half of them had... No, so half of them have... Yeah, that conflates 2 cases, unfortunately. But it's not just... It wouldn't just turn into 0, 1, 2, 0, 1, 2, 3 mod 4. Those aren't quite the cases. Because in the 2 mod 4 case, I have follow-up questions about what happens when you take the factor of 2 out. Do you get something that's 1 mod 4 or 3 mod 4 as your odd part? It could be either. That's disappointing. We almost simplified the table to be just mod 4. Yeah, so the rule for quadratic reciprocity, maths, the rule is that you get a minus sign only if both the primes that you're turning over, if they're both 3 mod 4. So if the PI is 1 mod 4, then you can flip that one over for free, no minus signs. So actually that means you can have as many of those as you like, and I'll just let you flip all of them. It's both. It's weird. It feels a lot like it should be exactly one of, but it's both. The rule is that it's both. There's kind of a product thing going on from the size of a rectangle, weirdly. Right, we saw a proof using a rectangle. The area of a rectangle was relevant, and that involves a product. So behind the scenes, there's something that's odd or even, and we care about the parity of the product. Often in life, I think you care about adding together odd and even numbers. So the normal kind of pattern is that you get this kind of thing like this, where you would say, right, okay, so the parity behaves like this, right? Whereas for quadratic residues, there's this kind of weird thing going on where we want the product, which behaves like this, which has a kind of weird exceptional case over here. I don't know why it's even on the inside. And the character of these tables is quite different. Anyway, pi over p1 if p is 3 mod 4, and pi is 1 mod 4. Yes. There's well, I don't know if it's 1. I know that it's the same thing as p over pi. Let's find it in here somewhere. So the rule, not proved on this page, but the rule is that for distinct odd primes, p over q is q of p unless they're both 3 mod 4, in which case you get a minus sign. And there's this both in here, and there's this kind of missing observation that in almost always, if at least one of them is 1 mod 4, you could say, then you can just flip for free. Yep, so the factor here is 1 if one of them is 1 mod 4 or both of them. And in our application, we have all of these prime factors pi, and the ones that are 1 mod 4, they get a kind of free pass. You can flip these terms over without worrying. You won't get any minus signs, because just having one of them being 1 mod 4 is enough to avoid this kind of case down here. So those ones just flip for free. It's the ones which are 3 mod 4 where you get nervous, because you look, oh my goodness, is the other one 3 mod 4 as well? Is p 3 mod 4 as well? And if it is, then you're in for a lot of minus signs today. If you're looking at prime p, in our application later on, if you're looking at prime p that's 3 mod 4, then whenever pi is 3 mod 4, then you'll get a minus sign when you try and flip that one. What did I mean? Yeah, probably I said something like that. I probably meant all the flips with PIs that are 3 mod 4, he says, because that's true. I hope that's what I meant, because I'm supposed to mean true facts. Sorry. Yeah, sounds like out loud I might have said something that had an or in here instead of both. Exclusive or. It's quite hard to get out of the mindset of how lots of these things would be just like, well, you just add up the parities, whereas here we're kind of multiplying. Okay, I'm going to have another look at 6.8, which was back here. And there was a lot of stuff in the build-up, which I feel like we did quite late on. Oh yeah, there was all of this as well about building prime powers to find out whether prime powers are quadratic residues. We're going to have a look at 6.9 again in a minute, I think. I wasn't quite brave enough to get the minus sign last time round, but maybe I will be brave enough next time round. Okay, so where did this even start? Should we go all the way back to start of 6? We could, couldn't we? No, that's good. Let's go here. Right. So 6.1. The divisors are represented. If n is represented, then you can. Oh, there's this previous fact before even 6.1 that if n is represented, then there is a form like this, and if it factors, then you can make it factors. Meme X wants a complete reset. It's only been about 6 months, right? If and only if delta is congruent to a square mod 4n. So this is our main fact, which is why I've been thinking about squares recently. Modulo some number. Some absolute minus sign voodoo going on over here, flipping things around, which makes me very nervous. No, it's fine. Multiples of putting a minus sign in that bit is fine. Actually, I've decided. Okay, so you can represent factors. So then, what are we up to around here? So we looked at small numbers for a bit, and that was fine. If two co-prime numbers are represented, then so is their product. This is going to build us prime powers. And we've used this thing about quadratic residues, which was fine. And then off you go and build these things, thinking carefully about any factors of 4, which is a bit awkward. But we go past it. There's the ice cube. And then we could build prime powers, provided you get a bit of starting. With 2, it's a bit different. You have to be like this. An odd number x is square 8, then x is also a square. You have to start with 2 cubed, and then you can go up to other powers of 2. And that one works by just trying to find a square root in a way, I think. Search through all of these, and I think the proof says that they're all different or something. Rewriting. Oh no, we're going to solve this using Bazoo or something. We have gone round and round a little bit, but that's just learning, isn't it? That's just trying to learn more things. Power of prey. Okay, so you make powers, you can multiply them together, and then we're all good. So we have these sort of small propositions that translate things back into the representation problem. That makes it a bit slower, but I'm doing all right. Okay, so primes are factors, so they're represented. And then if a prime divides this, but not the conductor of delta, then no form represents p squared. So this is the thing about not being able to represent things, which I'd like to reread because this separates things out. Separates out the cases. This is kind of different, isn't it? Can I remember what the conductor is? Probably not. Let's go. Primes dividing delta is fine. For primes dividing delta, yeah, good, okay. P is odd, yeah, okay, fine. If P is 2 and divides this, then we're good. Okay, suppose P is a prime, where are we going with this? And some form of discriminant delta represents P squared. This form is equivalent to this. Since P prime is must then divide B, so in fact P squared divides B squared. For P squared divides this, and it's part of the conductor, which I've remembered is this factor out the front. Okay, now where are we going? Consider first the case that P, yeah, factor of multiple out here, out the front. Consider first the case that P is odd, then P squared is 1 mod 4, so delta is delta prime mod 4. Oh, we're still going. Delta prime is also a discriminant, so by the definition of the conductor, P divides the conductor. Goodness me. So if P divides delta but not the conductor, then P squared cannot be represented by any form of discriminant delta. What on earth is going on? We're out of water. 10 to 5. Yeah, I think I'm trying to read this too fast. This is hard. Can I just accept it and move back to where I was? P squared is not represented, then higher powers would have that factor. So factors of n are always represented, so you can't do higher powers or multiples. Okay. Multiples or higher powers are a sort of multiple. Can I just accept this briefly? Each prime dividing the discriminant is represented in discriminant this. If a prime divides delta, but not the conductor of delta, the conductor is not just the square part, is it? Because when you take out the square, you are supposed to be left, when you take out the conductor, you're supposed to be left with delta prime of discriminant. Here it is, such that you can take out this. You take out a large square, but you're supposed to be left with a discriminant, which might be 1 or 4, 1 or 0 mod 4. It might be 0 mod 4, especially if if it's 0 mod 4 and you consider taking out an extra factor of 4, then you might be left with something that's not a discriminant. It's 3 mod 4, depending on the odd part there. Right. Okay, I'm going to take it for now, I think. And I think I just haven't understood conductors at all. Or haven't understood, given delta, how do I identify the conductor? Because I would just start taking square factors out at random. And no, because delta was anything that's 0, 1 mod 4. So we're sort of taking out the square parts. But if you see something that's 3 mod 4, or no, 2 mod 4? Yeah, 2 or 3 mod 4, you kind of panic and you put some factor back. Okay. And then putting all that together, you have this problem. Right. So here it is then. Product like this of powers of distinct primes pi, each of which is represented by some forward described delta, with the restriction that you can't do. You can do factors of delta, but you can't do squares of those primes. That would be silly. Because something about conductors. You can't do squares of those primes. Of course not. Those primes divide delta. But it says fundamental. It says fundamental. So prime can't divide the conductor for fundamental discriminants, because fundamental discriminants are the ones with conductor 1. I think. Yeah, I want to check out the odd prime squares. There's something like this near the top of a page about 20-30 pages ago. I'm not going to go looking for it, but you can do something like taking out the odd prime factors. Right. For fundamental discriminants, then, the situation is actually much simpler because the conductor is 1. So this fact up here is all about you're often in this case where the prime divides delta, but not the conductor, because the conductor is 1. Taking out p squared wouldn't give you a discriminant. I want to reread that side again. Where's the punchline here? Suppose p is dividing prime dividing discriminant in some form. Suppose you could actually do p squared. Then you would write this, and the prime would divide that, so the prime would divide b squared. In fact, p squared divides b squared, and p squared divides delta. You can bring out the factor. Because p squared is 1 mod 4, so this is fine. You're left with something that really is a discriminant. I mean, if you're a fundamental discriminant, then that's already a contradiction, because you're not supposed to be able to bring out a prime, I guess, a square factor out of this thing. Yeah, okay. Oh, we're a separate case for p equals 2, but this bit we're 1 or minus 1. So then you have a discriminant, so then it divides the conductor. If p is 2, then everything's even, so, oh gosh, think about even numbers very carefully. Oh gosh, look at some squares. Wow, really? In both cases, 2 divides the conductor. Right, okay, this case feels totally different, but this is the important one, I think. That just chasing it through, if p divides delta, then p squared divides delta. That's mad, isn't it? If p divides delta, then p squared divides delta. So you'd already taken out all the fundamental, looking at a fundamental discriminant where you wouldn't be able to remove a factor of an odd prime squared for fear of getting a smaller discriminant as one of your factors. Fundamental discriminants don't do that. So they can't make p squared for their own prime factors p. Even if it's like 40 is a multiple of 2 squared. You can make 2, but not 2 squared. 2 is a bit different because then 2 squared wouldn't be enough, but 2... whatever. I feel like this bit, 6.1... Nope, 6.1 works for 2 as well. We don't have to think about 2 separately. Right, okay, odd primes, even primes, all going on all at once. Okay, that was a statement about which things we can make for fundamental discriminants, which feel like the easy ones because they have conductor 1, which means that as soon as you pull out a prime factor, klaxons go off. And you say, oh no, can't happen. I'm a fundamental discriminant, so I don't have any of those factors. I know what a factor of a conductor is. My conductor is 1. It has no factors. Prime factors. No odd prime factors. Right, here we are. We're down here, and we've now developed, so fast forwarding again, back up to where we currently are, we're now at this point where we've got a big fact about which things we can make. Involves thinking about whether -1 and 2 are square numbers, modulo prime p, if you're trying to make a number p, and also the other prime factors of delta. So we're looking at theorem 6.11 now. There's a lot of text on screen. Let's try and break it down. It's considerably more complicated. Danger, danger. The book link. It's what, because it's what we're doing. You're reading this. Sorry, I missed the link. I missed the thing. There you go. Ah, yes. Okay, good. Okay, here we go. A number like this is represented. Well, greater than 1. Representing number 1 is a bit boring. Yes, I've thought about it, I don't want to represent it. It's represented by at least one form of discriminant delta, exactly when n factors is a product like this of powers of distinct primes pi, each of which is represented. You have to be able to represent the primes pi for some form of discriminant delta. We're saying this phrase quite a lot, where it's the most 1 for primes pi dividing delta, like in theorem 6.8. But not, sorry, primes that divide delta but not the conductor. So here you might look at the conductor and say, actually p squared does divide the conductor, so maybe it's all fine. Well, for primes p dividing the conductor, the allowed exponents are given by the following rules. Oh no, here we go. But maybe it's fine if I divide the conductor, right? What could go wrong? Here we are. First, write delta p to the sq with p to the highest power of p dividing delta. Right, we're trying to write p, and now it matters how many of them you've got. You want to try and write some prime power or some, product them together, so it'll be fine. The highest power of p dividing delta. Then if p is odd, the allowable exponents, oh my goodness, there's 2 as a special case later on down here. If p is odd, the allowable exponents e are those for which either is not too big, not too large, or greater than s if s is even and q is a quadratic residue modulo p. Oh my goodness. The other bit has to be a quadratic residue modulo p. That's mad. So you can go, you lose half of them, provided q is at least a quadratic residue mod p for the large powers, I guess. What does that remind me of? So adding 2 to the power reminds me of multiplying by p squared, which seems fine. That would be allowed if we're talking about quadratic residues behind the scenes. Multiplying by p squared gives you a square, right? I hope. But somehow in there, this q over p problem is worse. What is going on down here? If the prime you're talking about is 2, if you're interested in whether you can represent the numbers 2, 4, 8, 16, or so on, then, well, don't go too far in that sequence. You can only go up to s minus 2, where s was the number of factors of 2 in your discriminant, which must have been Well, no, I mean, if your discriminant is odd, then this doesn't say anything at all, does it? You're not allowed any. We're talking about primes that divide delta, so delta is even. So I know you have a couple of them in there, but you need at least 3 to play. Or if you have an even number of them, then you're allowed to have some more fun. It depends on QMod 8 though, and there are 4 cases, so you could have all of them. Maybe you could just get a bonus 1 or 2, or maybe only 1. What is all this? Mary says it is tea time because it's 5 o'clock, so it's time to have a cup of tea. And Matt is requested like a totally different book, which I'm going to stick on this one for today. I would like to know what on earth is going on. At least the gist of what on earth is going on here. I don't actually know if the proof is coming up next. Are we getting a proof next? Examples will be given following the proof. The main part of this is contained in a lemma, and the lemma looks like quite a big pile of number theory, followed by there's the proof of 611, which is going to go on for several pages. And, oh no, it stops here. That's not too bad. And then examples. That's all right. We've got a sort of solid page of maths. So we're going to go PTO 2 lines. There's a couple of lines on the next page to do a lemma and then 6.11. And then we're into example mode, which we quite like. We quite like example mode. And it looks like it tells us everything, because if we do fundamental discriminants and non-fundamental discriminants, then we're good. Of course, we might start to wonder. loads more stuff to prove later on. We might start to wonder which quadratic form produces each of these primes, or whether, I don't know, whether the forms are primitive. Yeah, okay. Oh, right, okay. This is good stuff, I think. After this, and then there's a big table, and then are we out? No. Unique representation, that's fun. H labels and Q labels again. And then are we done? Another interesting fact. We're into some sort of bonus facts. Oh, look at this. This is lovely. There you go. What a nice fact. Wait, is this like a list of primes? What's going on in this proof? Representing 1. I'm going to assume C is non-zero. Right, okay. Any finite list of primes, allow repetitions. The P be the product, consider the number this. 1 plus BP plus CP squared. Amazing. This is represented by Q since this is a primitive pair. If K is large enough, we will have n larger than 1. Okay, so we can win. Any prime P dividing n will also be represented by some form of discriminant delta, but this P must be different, since dividing Pi into this gives a remainder of 1, whereas P divides n exactly. This is sort of like the infinite primes proof. This is really cute. Any finite list of primes, there is another prime. It's a large number, and you must be able to represent its factors. So that's kind of fun. Right, quadratic residue in 205. I don't know. We're going to get through to 189 today? Probably not. I think we're going to get through. Well, to be honest, I think we're going to read one more page and then give up. No, I think we'll have a go at these. This page of proof, which looks quite hard. We need to do lemma 6.12 before we do the proof of 6.11. It does look hard. We're trying to prove something really complicated. Then we get genus as a treat afterwards. 10 pages, 15 pages of genus, and then we're back to quadratic residues. So that should be 4 or 5 streams, right? Let's make a cup of tea. That makes me feel better about the whole thing. We're not giving up. We're just making a cup of tea. That's allowed. Right, back soon. I'm going to run an ad break. If you see any ads during the ad break, then you're supporting charity, very long term. If this stream ever cashes out, then it's going to charity. If you make a cup of tea, then you might miss the ad breaks. And if you, for any reason, don't get any ads, then I'm afraid all you're going to see is a screen that says back soon while I make a cup of tea myself. Feel free to go and get a glass of water or a cup of tea yourself. See you back here in a couple of minutes. Hooray! I think I'm back. Right. Yes, okay. 6 ads. 6 ads for Murray in chat. My goodness. Can I find out how much I raised overall? Let's have a look. Monetization. Where do I click? How are we doing so far? I've done the onboarding. By watching all of these adverts, what have we raised? I'm not allowed to cash out until we hit a certain amount. Can I find out? Where's the button? I used to be able to find this button. I don't want to change my payout method. No, can't find it anymore. And I don't think that me looking for it is very good TV. Yeah, Mary has done quite a lot of bits and what have you done? Quite a lot of ad breaks and cheering. Definitely used to be in here. Oh, right, okay. Oh, yes, good news, chat. We're only a couple of dollars off. The threshold is $50. We're getting to $50. We're going to get to $50 one day. We're currently at $48. We've been streaming for about 2 years. Like the fireworks that are going to go off when we get to, well, not expensive fireworks because that would defeat the purpose, but the fireworks that are going to go off, it estimates that we will get there in about, oh wait, no. Yeah, they estimate that we've got 2 months to go. That's really funny to me somehow. $2 is like, for a while I had 1 subscriber, much appreciated. But for a while I had 1 subscriber. I'm not sure what the subscribing gets you, but sort of like possibly 1 subscriber. Slowly bumping towards $50. We don't get a big cut from ad breaks. Right. For example, I think that ad break, shall I give you a number? Right, so for our, we had a Prime subscription, which got, I'm looking at in the last month. So in June we didn't have a Prime subscription. We got 20 cents from watching ads, and in July somebody's done a Prime subscription, so thank you. That gives us $1.80, and we've watched 36 cents of ads. So the ad breaks, that's like 4 streams a month as well. So pressing the ad button is about 9 cents, which I think is not even 9 pence, is it? Possibly. What am I doing? You and me both, Mary. Right. You don't need to subscribe. You really, I know everyone sort of says that a bit, but goodness me, don't subscribe to this unless you actually want to. Right. Okay. Maybe I should do a stream push. Well, like 2 scripts. Never mind. Right, okay. Sorry, Twitch is now giving me other notifications. I've shown an interest in money, and now Twitch wants to give me all the money options. What are we doing? We're learning about quadratic residues. It's good for us. That's priceless. Maybe. Right. Here we are. At Lemma 6.12, gathered here today to find out whether you can write particular things as squares, modulo other numbers. Suppose the number x divisible by a prime p factors like this. Well, that's the thing in the proposition we just saw. P does not divide q. You took out all the factors of p you could find. Yes, there you go. Then here are some facts. Oh, charge this. Interesting. Let's see if that just goes away. X is a square mod p to the r for any smaller r. Interesting. This is going to translate. This is going to be another pair, right? Where we prove something about quadratic residues and then we apply it to representing things with quadratic forms using the translation device we have, which says, or it almost goes 1 to 1, except there's a factor of 4 you need to worry about, which means that it always gets presented as a separate claim, but it's fine. It's a little bit fiddly to track the factors of 4. Right. That was the closest I've got to asking people to subscribe, and then I backed out of it and asked people not to subscribe. Not very good at this commercialization thing. Oh, t-shirts. T-shirts. No. Right, okay. So this is going to tell us the same facts, but about whether things are square or not. Quadratic residue is a phrase we use as well. It's the same thing, right? You can do the ones that are smaller powers. If R is greater than S and S is odd, then no. But if R is greater than S and S is even, then yes. And that looks like we're talking about... Oh, well, we're not just talking about odd primes, any prime. Any prime. No special case for prime 2 in this lemma, but there we go. Okay. So all the complications are going to be from that translation factor of 4 then. The translation factor of 4 has got quite a lot of impact on the complexity of this statement that we just saw before the break. Okay. Part A is easy. Oh, okay. If you say so. X is a great big factor of p to the has a factor of p to the s, so it is 0. So it's a multiple of p to the s, so it's also a multiple of p to the r, and 0 is always a square mod anything. Good, this book is finally talking my language. Look at this, that's the sort of nonsense I would say out loud. Always a square mod anything. Good, you can do the small ones because you are currently 0 mod these things. What number shall I have in my head? I'm going to have it in my head 3 to the 4 times 11. That's quite a large number. So is x a square mod 27? It's 0 mod 27. Yep, good. Is it a square mod 9? Yes, it's fine. Is it a square mod 81? Yeah, because I'm still a multiple of 81. So modulo this is 0. Good. Okay, easy. For B. Now keep going. Is x a square? This is odd. And this is even if and only if q is a square mod p to the rest of it. Okay, here we go. Here we go. It's surprisingly hard to read the statements. Let's see if we can prove them together. Here we go. For part of B, we assume r is greater than s and s is odd. And we're going to try to prove that x is not a square mod p to the r. The book says, suppose this is a square mod p to the r. So it's like this, eh? And it's y squared plus some multiple of p to the r, right? With r greater than s. Then p to the s divides, well, a lot of stuff. And it divides lp to the r since you have loads of p's over there. So p to the s divides y squared. Since s is assumed to be odd, or here's the odd even stuff. Since s is assumed to be odd, and the exponent of p in y must be even, this implies that p to the s plus 1 divides y squared. Okay, there must be at least one more prime p in there. It also divides lp to the r, since r is strictly greater than s, so at least as large as s plus 1. So from the equation this, we conclude that p divides q. Oh, there's an extra factor of p on the left. Oh, problemo, because you said you took out all the factors of p. No more. This contradiction shows there's not a square mod p to the r when r is greater than s and s is odd. So statement B is proved. Okay, that's not too bad. It's not too bad at all. S is odd. Okay, well, so in my example number up here, s is even, so I have to read this much longer statement. But let's try and chase it through for 3 to the 5. Is 3 to the 5 times 11 a square modulo 3 to the 8? And the answer is no, because if that's a square modulo 3 to the 8, then just chasing through some numbers, see what happens. It's good. You've got this shared factor, so we can't just use our quadratic reciprocity facts. We have to chase through some factors of 3 to say, well, no, because the square. Yeah, so over here, we'd say you're squaring something plus some massive multiple of 81 would give you this number. Then 3 to the 5 divides that square, so 3 to the 6 divides that square. The square would actually be a multiple of 3 to the 6, because you squared something that was a multiple of 3 several times over. And then this would be a multiple of 3 to the 6, but that's not a multiple of 3 to the 6. Okay, that sort of thing is what's going on. And then for our next trick, we're going to think about 3 to the 6 times 11. Good. Oh, Matt subscribed. Oh, thank you for the subscription. Oh my goodness, you didn't have to do that at all. I think that might be, well, we'll see. That might be the subscription that, oh, I'm sorry, I had notification sounds turned off. I mean, then I missed the notification on screen. There, give us a go. There we go. In chat. So excited that I just banged my wrist on the table. Ow. Right. I wondered if the RFLs were for the prime numbers, but no. Right, there we go. Take your screenshots now. Everything's gone away. No, it's back. Okay. So, one last case. We've only got that much before we get to a line, which is a good moment, a good pause. For C, assume that you're looking at this thing, and this is even. I can already kind of see we're going to follow the same things, aren't we? We're going to follow the same steps. There's going to be some squares. We're going to divide by some big power of p, aren't we? Here we go. We have an equation like this. Plus p to the s divides y squared. S is now even, so y squared is like this. Cancelling the p to the s. Yeah, we're going to cancel it out. Okay, so we can bring out all these factors of p to the s. Yes, from y squared. If that's an odd number, then you're going to have another one so that you get the square number, but then all problem on the left. Anyway, okay, good. Even number, great. Y squared yields an equation like this, which is all about whether q is a square mod something else. After you've done some division, so I need to remember this as division. P to the r minus s. With an equation like this, and hence this. Oh, so this is conversely, if q is a square, we have an equation like this, fine, and hence multiply up. Since s is even, it says that this is a square. Okay, the square thing is preserved. Right, okay. P to the SQ is a square mod P to the R. Oh, look, you get a little star next to your name, or on that screen above your name as well. Wow. Maybe I want to subscribe. Okay. It says that P to the SQ is a square mod P to the R. Yeah, cool. Okay, nice. It's all about squares, isn't it? So where did this R minus S turn up? Was there an R minus S in here? Not quite, but maybe this will turn out to be... Where's this going to come from? Haven't seen one of these yet. But it's talking about whether... Oh, S is even. So the question whether Q is a square, P to the R minus S. Which is a bit like E minus S. No? Yeah. This says you can keep going forever. Keep going forever, but only the ones. This is independent. This fact is independent of E, whereas I'd expect the P to the R stuff to be dependent on E, which is a bit of a surprise. Let's see, is this the right sort of cable that I could connect? No, that's the wrong sort of cable. I'm going to quickly fetch a cable to fix the problem in the right hand corner where this thing is dying. I'm going to be back in a second for translating this proof that we've just seen, translating it into discriminant facts, which is down here. Yeah, okay, which is about powers of primes, but this thing is dying, so I'm going to fix that. We have an unusual second pause. Should have got this over the tea break. Back in a second. Technical difficulties. And back again, I think. It's gone away. We fixed the charge problem. There we go. Right. What a stream. So professional. Right, okay. As in the proof of theorem 6.8, which was quite a while ago, we just had a quick look at it again. But we were looking at whether, so for fundamental discriminants, we looked a bit at whether you could write particular primes, think about the separate primes, and we've now got this property that, is this relevant? I think this is relevant. So if you're thinking about a particular discriminant delta, no, it's not quite, that's not quite true, is it? If I'm thinking about, yeah. So if I'm thinking about a particular prime, and then powers of primes, there was quite a bit of maths on screen to work out that you could do this for, if x is a square mod p to the r, then it's a square mod p to the r plus 1. Yeah. But r greater than or equal to 1, unless we're talking about 2, in which case it's r greater than or equal to 3. Okay. All powers of primes not dividing the discriminant delta are represented if the prime itself is represented, which seems like still a hard question for which primes are represented. Proposition 6.7, we know that primes p divided this are represented, and their powers cannot be represented unless p divides the conductor. For the remaining case of primes dividing the conductor, we'll apply the preceding lemma with x equals delta. It was the discriminant all along. No one saw that coming. Oh yeah. Yeah, so the pause was a charging cable thing, by the way. We're using cool technology. Right. Proposition 6 was it when p dividing delta represented. That was just true for all discriminants. As p divides the conductor. And then dividing the conductor is going to be, sorry, flipping back again. Dividing conductor is going to be this second part here. Following rules for primes dividing the conductor. Okay, let's see how that stitches together. Off we go. For odd p dividing delta, we need to determine whether when delta is a square mod p to the e. Yes, please. By the lemma that times this happens when e is less than or equal to s. When e is greater than s, and this is even, and q is a square mod p e to the s. So here we go then, because the whole question is about whether delta is a square mod p. I think for odd primes, yes. Now the question is, you can ignore the factor of 4 and just focus on the question of whether delta is a square mod p. Okay. By the lemma, the time this happens when e is less than or equal to s, Yep, so up here, scrolling back up again, up here, when the exponent is not too large, or when it is large, but the power in delta no, is even, you need the power of p in delta to be an even number, and you need the leftover bit to be a square mod leftover p to the other stuff. Oh my goodness. Or when, and then this complicated third case. When e is greater than s, this last condition amounts just to q being a square mod p by, oh gosh, a lemma from ages ago. When e is greater than s, this last condition amounts just to q is a square mod p to the e minus s. Is q a square mod p? Oh, this lemma is about building prime powers, and because you can always do factors, and then if you do one, then you can build this big power for odd primes. That lemma 6.5 was kind of good. So in other words, the question of whether q is a square mod this big prime power is just a question about whether q is a square mod p. So you need that thing to be +1. It's precisely that. Right. Maths to ask a question, and the answer is yes. Bits, I think, have some cache value. I've only ever got about 10 bits total or something like that, I think. They have a cache value, and it all just gets added together. There's a complicated pie chart somewhere in Twitch. The key idea is that if any money ends up in my bank account from this, then it goes to charity. Maybe it was Zoe who gave me bits. I'll believe that if you say it confidently. If you're watching Zoe or somebody else. Oh dear, here we go. Okay. 2 is more complicated because powers. Yeah, so the 6.5 is more complicated for the prime 2. Half cost, okay. Half credits, sorry. I don't know what to do with bits. Sort of in-game currency, aren't they? Although Twitch seems to have quite a few sorts of in-game currency, so here we are. Right, we need to determine where delta is a square mod, and then there's this. We're not allowed to ignore the factor of 4 anymore. The rule is actually whether delta is a square mod 4n, and separately we could ignore the factor of 4 if p is odd, because you can look at the co-prime bits and then multiply back up together again with Chinese remainder theorem or something. But here you can't ignore that if the prime p that you're trying to make is even, if it's the number 2, then you've got to have this factor of 4 in there as well. We've got to worry about this. Oh, but this just changes the left-hand side, because the lemma at the top included 2. So this is more like an e plus 2. So I should really think about this as e plus 2 being at most s, to compare it with the thing we had before. Or when s is even and q, an odd number, the odd remainder bit left over once you've taken all the factors of 2, is a square mod 2 to the, oh crikey, what is this? Oh, you have to have the +2 in there as well. This multiple of 4 out the front again. If e is s minus 1, and e plus 2 minus s is 1, every odd number is a square mod. All of that is 2, so you're fine. If e is equal to s, then you get this. And q is a square mod 4 only when, okay, here we go, 2 more lines. So here's some more cases. What's going to keep going is as e gets larger, this is going to be larger and larger powers of 2, right? We're looking at the case, is q a square mod 2? Yes, it's an odd number. Is q a square mod 4? Depends. And then is q a square mod 8? It's an odd number. Might be, might not be. Depends a bit. And then is q a square mod 16? These questions feel like they're going to get harder and harder. Final 2 lines then. I'm going to read them, sorry. Sometimes we try and predict what they're going to be. And it seems like it needs to get harder and harder. Yeah, so there's this bit here, 4k plus 1. And if e is larger than that, then e plus 2 minus s is greater than or equal to 3. So we're asking whether q is a square mod this only when it's a square mod 8. Is that if and only if? What is this? So apparently we're now done. I don't feel like we've captured all of this complexity in the table down here. This tells me when to stop. That if q is right, okay, so if q is 1 mod 8, then all of these questions, is it a square mod 16, is it a square mod 32? If q is 1 mod 8, then we've got quite lucky because, well, it'll be 1 more than a multiple of, no, I was guessing, well, no. It won't be 1 mod 16, will it? Yeah, I'm not sure I can tell if q is a square mod 16. I don't know how we're getting this all. I'm happy with these ones, I think, because I can see from the properties that we're all right. You're just asking whether something is a square mod 2, or maybe if it's a square mod 4, and I'm still happy that this is a square mod 4. These ones are squares mod 2, but not 4. I don't know why this one's good for all of them afterwards. I mean, keep going. You can make all of these exponents. Oh, right, it's lemma 6.5 again, isn't it? It's lemma 6.5 again. You can make all of them. So I understand that. Ah, right, okay. Not at all obvious to me, but is, I think, lemma 6.5 that if you're a square mod 8, then you're a square mod 16? Well, the only odd squares mod 8 are 1. So what am I talking about? The fact apparently is that if q is 1 mod 8, then for any power e, let's look at it again. For any power e, q is a square mod this only when it's a square mod 8. So this is about the prime powers again from lemma 6.5. I've got to remember we're using lemma 6.5. Only when it's a square mod 8. Which almost means, for odd numbers at least, that almost just means it's 1. Q is a square. Do I believe lemma 6.5, right? Lemma 6.5 has got this quite a big claim, I think. What are the squares mod 16 then? So the squares mod 16, the odd ones at least, are they precisely the numbers that are 1 mod 8? They're 1 and 7. Yeah, maybe they are. I mean, can I think of anything that squares to 7 mod 16? That's kind of the converse question, so maybe that's a bad thing to think. What am I doing? What am I doing? Let's try squaring some odd numbers mod 16 while looking at theorems lemma 6.5. We're going back a bit, I think, but it turns out 6.5 is really important. So I'd like to know it, I think. Oh, right, it's all a bit mixed together here. 4, 3, down. 6. 4, 5. Okay, here we are. For an odd number, if an odd number x is a square mod 8, mumble, if an odd number x is a square mod 8, then it is 1 mod 8, right? Quick check. 1, 3, 5, 7, square them. 1, 9, 25, 49, they're all 1 mod 8. So this is quite a strange statement, right? If an odd number x is a square mod 8, just means if x is 1 mod 8, then x is also a square mod this. Well, obviously 1 is a square mod anything you like, so we're good. So how does that proof work? For 6.5, does it just? Would you just prove? Did I just do it? Did you prove that if an odd number is a square mod 8, it's one mod 8. So then it's a square mod whatever you like. Write anything in there. What? Keep it chill. Here we go. When p equals 2, this argument is really complicated. What is all of this? What is all of this? What am I doing? I think this is just a fact about the number 1. What's all of this? What is all of this? I think I'm claiming the solution is always. I think I'm claiming the solution is always the number 1. Oh, maybe it's better than that. Maybe it's better than that. Maybe it's sort of, you can get from squares mod. No, that definitely says 8. That definitely says 8. If an odd number x is a square mod 8, there are not very many of those. Then x is also a square mod 2 to the r, for which r greater than 3. I sort of think this might be a fact by the number 1, and if we just check the squares mod 8. I mean, the prime p equals 2 is a special case, but it's a very special case. Good news, we can just find all the squares mod 8, work out which numbers we're talking about. It feels such a trivial fact now. What am I missing? There's not any more squares mod 8. I just found them all. Square your odd numbers. Off you go. 1, 3, 5, and 7. 25 is one mod 8. 49 is one mod 8. It's a famous fact that 1 is the only odd square mod 8. Yeah. But why is the proof so weird? Right? Five is square mod 4, but not mod 8. Yeah, that's true. So why is the proof so weird? Pulling my hair out. Right. What was the proof for odd p? For odd p, it's quite complicated. It sort of finds a square root. It's constructive. So for odd primes p, we're trying to find a number z such that x is the square of z mod p to the r plus 1, just a little bit. We're using induction to build up our prime powers. And of course, for odd primes, maybe there are loads of quadratic residues. X could be coprime quadratic residues. Just mod 8, there's not very many. We will look for a z with z is y mod p to the r, or in other words, like that. So why not choose, yeah. So we're trying to choose k carefully. And if you try squaring this, then you get all of this mess. And you would like this to be a multiple of p, which means really you would like this to be a multiple of p, which if you rewrite it, means that you would like L to be like this, which is a linear Diophantine equation with unknowns k and q, but that's fine. So you can actually go and solve this and find a kind of square root z by choosing L, or finding k and q very carefully to solve this equation, and then you get your value of k. So what do I think happens when p is 2? You have this equation, but by the way, I think it's always the case when p is 2, I think it's always the case that x is 1 and z is 1. I think that works. Oh, I've made my hair all fluffy. So let's try and read this and see if that works. L like this becomes this. We will not have a solution when L is odd. What's L? Oh my goodness. X minus y squared, p to the r, L. So if it's the case that you need an odd multiple of p to the r to get this to work, which I suppose I have this being yes, I think I'm claiming that x has to be the number 1, or 1 mod 8 or something. So maybe this does work. If x is 1 mod 8, then we're sort of worried that. No, this is better than I've been saying. Because what about 9, right? 9 is 1 mod 8, but the claim here is good. The claim here is that 9 is a square mod 16. That's true, that's 3 squared. Which I wouldn't be able to work out with my 1 fact. This is better. I got distracted by the fact that 1 and 9 are the same thing, mod 8, whereas this is just telling me that any odd number like 9, which it's kind of trivial, that's the same thing as 1 in the mod 8 universe, but this is also telling me that x as 9, not as 1, but as 9 is also a square mod 2 to the r for each r greater than 3. Brilliant, okay, take it all back, this is a good fact. Stop the clock at about 5 minutes or so. Right, okay, z's not always 1, x is not always 1. We might be talking about a number that is congruent to 1 mod 8, but we're talking about all of those. And as you increase the power of 2, those sort of stop being congruent to each other. So 1 and 9, the same thing, right? 1 mod 8, but then mod 16, ooh. And going one more, let's go one more. So 17, let's talk about that one as well. 17 is a square mod 8, because 1 squares to 17 mod 8. Doesn't sound true, but 1 squares to 17 mod 8. But then 17 is a square mod 16, which, fair enough, right? Like 17 is a square mod 16, what does that even mean, right? Like, it's still 1 mod 16. But the 17 is a square mod 32, because 7 squared is 17 mod 32. You have to do a search to find it, and there's a rule on the next page how to search. Okay, I've approved this a bit more. We're saying ice cube because there it is again. We're back here at the ice cube. This is 6.5. We've decided that it's cooled. We have an ice cube next to it. It tells us not just about the number 1, but exclamation mark x equals 9 counts 4p equals 2, not just 1 smiley face. There we go. Yes. So in particular, 257 is a square mod 1024, because 257 is 1 mod 8. It's 1 more than a power of 2, isn't it? It's 1 mod 8, so it must be a square mod, and then you can make the powers larger from there. I don't know what squares to 257 mod 1024. Should we try and use Desmos to find out? It's all Desmos question, isn't it? What squares to 257 modulo 1024? Oh, that's not really worked. Yeah, there we go. Okay, and then I'm supposed to go up to 257. Why is 257? And then really I only want integers, so I'm going to go numbers from 1 to 1024. And I'm only going to square those in here. And then the question is, that's a list of numbers. I want to plot those next to the numbers n. So we get these numbers. The question is, what squares? Oh, there's one. So this search for square roots in Desmos is just like looking for numbers on the line. Apparently 129 squares to 257 mod 1029. Oh, is there a pattern there? I mean, that's 1 more than a power of 2, isn't it? It is 1 more than a power of 2. Something's going on there, isn't it? Let's not think about it too much. Well, let's quickly think about it a little bit. So this apparently squares to 257. Yes, it will, won't it? Because this is 1 plus 2 lots of 128. There's your 257 plus, and then I reckon this will be some huge loads and loads of 2s over there. So modulo 1024. Who cares about that? So the rule is going to be something like sometimes you can get away with subtracting 1 and dividing by 2, and then the square is sort of this bit over here. Yeah, for powers of 2 like this. Good. Okay. There is a cool Pythagorean triple involving powers of 2 ? Well, I mean, we're working modulo arithmetic, so How much do I care about this? There's some weird multiple in here that's no good, right? Yeah, mod 1024 is not going to be very helpful, is it? Guess how cool do you think this is? Not very cool, I would say. Oh, you're telling me that separately there exists one. I see. Okay, not based on this. Right, okay, good. I've understood 6.5 a bit more. I'm going back in. I'm going back in. Here's the bit where we started. It's also where we started last week and the week before. We're back in over here now. Good. Is Q a square modulo this large power of 2? Well, only if it's a square mod 8, including things like 1 and 9 and 257. Those are good, which means that Q is mod 8. Amazing. Those are the cases where you're allowed to continue forever. We've now hit the square box at the end. I think we've understood this. It says that depending on whether Q is 1, like this, 1 mod 4 but not 1 mod 8, you might be able to get an extra factor in there. If not, then you have to stop here, and if you hit 1 mod 8, then you're good. You're set for life. Lemma 6.5 properly tells us that we can do all of that, which means that we've now seen enough maths, including fiddly powers of 2, different because Lemma 6.5 is different for p equals 2, means that we're now, I think, done on theorem 6.11. It looks hard, but really the complexity comes from 6.5. Good. I thought that page was going to be really hard to read. It was actually fine. It was all 6.5, and I'd misunderstood 6.5, or not really thought about 6.5. I think it's RFL time. It feels wrong when I say that. Yeah, RFL. Oh, there we go. The colour changing one. It's also massive in Twitch chat. Amazing. Yeah, it looks hard, but it all goes back to first principles, or where did this come from? This book's always like this, right? There's always building things. Not always in chronological order as you read the book in front to back, but it is building things. You made it enormous as well. Good job. Right, okay, just appreciating a large emote in chat. Good. Okay, that right. That was 30 bits. Oh my goodness. Well, can't say the stream hasn't achieved anything. I have some understanding of squares modulo 1024. Here we are. Right, okay, we're going to have a quick look at some examples. More subtle possibilities in the preceding theorem. Rather simple forms, x squared plus ny squared. Oh, is there a book called Primes of the Form x squared plus ny squared? Is that a book? Like a Yellow Springer book? Maybe not yellow. Yeah, okay, so this is what we're doing, right? I can't show you that because it's got my postcode in. Right, okay, I found it on Amazon. There's a book called Primes of the Form x squared plus ny squared. Okay. Primes of the form x squared plus ny squared. Fermat, class field theory, and complex multiplication. 3rd edition with solutions. What a fun book. X squared plus ny squared. I think one of my friends had that in 4th year, I want to say. Right, okay. Well, maybe that's sort of what we're doing. We're asking which primes are represented by this form. X squared plus ny squared. I don't think my charity count updates that fast. Let's check anyway. It does not update that fast. Yeah. I wish. It would be obviously great if you were watching a stream and people were cheering and chat was going really hype and the streamer was cashing out in real time. You can imagine that being really popular as clippable content. I don't think it's happened though, that anybody has like gone on a sort of hype train and also managed to withdraw the cash live. Look, chat, you sent me money over the internet. That would be the clip, I suppose. So we'll just stream us. Anyway, yeah, it'd be like an IRL live stream. The synergy would be you do it IRL on the street, and you get someone really flash with their cash, and they'd be provoking donations, and there'd be all bits and cheering and stuff. But they'd be out on the street by an ATM or something, so that they could do like the redemption and then withdraw cash. And or I don't know, maybe it's Mr. Beast or something, because then they don't like hand it out to people or something. You've got like weird bit to bank transfer to cash money cycle going on. There's this kind of fever dream for you. I know, Twitch nonsense. Right, nobody's cashing out today. Oh my goodness, what a weird setup. I knew that doing this on Twitch would be just weirder than YouTube. I just can't imagine all of this like auxiliary nonsense. Just don't think YouTube's like that. Right. Okay. Yeah, so what's the donation tier for deciding which book I'm reading? Oh dear, it's all gone a bit silly. It's 5 to 6 real time. Let's see. Okay. -4 is sometimes not a fundamental discriminant, such as when n is congruent to 3 mod 4. Because... Wait, well, sometimes not a fundamental discriminant when n is 3 mod 4? Is that okay? Oh no, because then this would be 1 mod 4 after you take out the minus sign and the 4. A minus sign in there is a bit of a surprise. Okay, I've got to remember, minus signs flip my intuitions about mod 4. Okay, even though that's multiple of 4, so I might relax. We're all about taking out factors of 4. When can you do that? Crikey. Right, 3 and 7. Those are some pretty good examples. They're both 3 mod 4. Off we go. Conductor 12, because you can take out a factor of 4 and still be left with delta is -3, which is still a discriminant? Question mark? What's our standard example of something with discriminant -3? I guess it's like b squared minus 4. So b squared minus 4ac is just this one, isn't it? That's got discriminant 3. 1 b squared minus 4 is -3. Okay. Good. Well, you can always do that, so I guess I should stop worrying and just do things. Okay. And the non-primitive form like this, 222. What's the donation tier where you get a quadratic form named after the digits in your username? Anyway, never mind. X squared plus 3y squared looks like this, and the primes represented here are 2. That one's represented by this form. 3, and the primes like this, where if you turn the handle, you see, so this question turns out to be, I guess the prime. Primes are always 1 or minus. What is going on here? Primes with this. Oh, I see. With this equals 1. It's a sentence. So these are the primes that are 1 mod 3. There you go. Oh, so this is actually a calculation to work out which primes are represented overall. The numbers represented discriminant -12 are the numbers like this. So theorem 6.11 is then good. So then we're off to the races. Because then we can just say, here you are, here are the numbers you can represent. You can do powers of 2, but careful, because you can't, you have to stop at s, because, long pause to think about the powers of 2. That is subtle. When we apply the theorem for this prime 2, we have s is 2 and q is -3. So be careful, everyone, and remember which of the subcases we're in. There are about 4 subcases of the second subcase of the special case for p equals 2. Each prime congruent to 1 mod 3. Okay, and then you're good. Those primes are represented. Right, okay. We can in fact determine which of these is giving these representations, and this is going to be what we're up to next. This which stuff is going to be the kind of journey that we go on next, I think. We saw a sneak preview a month ago where we looked at how there's some structure to whether it's Q1 or Q2, and there's some sort of group theory to tell you which one. You possibly have to split these down by thinking about mirror images separately, like complex conjugates or something, to discover the structure of what's going on. Okay. Form Q2 is twice this. We've already determined this, have we? Okay. Products like this. Oh, because that one is fundamental. So for that one, you can... That one's primitive. The discriminant is fundamental because it's -3. Can't pull any squares out of that. For each prime like this. If the numbers represented by Q1 and Q2, the numbers represented by Q2 are those with A equals 1. What about these 2's? None of the numbers with A equals 1 are represented by Q1, since this is never 2 mod 4. That is true. Good fact. Right. -28 as conductor 2 again. So there are these. That's a pretty similar situation, but now 7 we're going to think about whether we're in a different one of the subcases for the prime 2 case. So the primes represented 2, 7 and odd primes, which like this, so mod 7 is the way to go. Oh, is that list of squares mod 7? 1 squared, 2 squared, 3 squared, and then you're done. According to theorem 6.11, the numbers, here we go, this is going to look really weird, are the numbers like this with B at most 1 because it's a factor, and other bit of 6.11. Can I remember the other bit of 6.11? You can't keep going because the other bit is not a quadratic residue or something. Each prime pi, each pi and all prime like this. No restriction on A, since when we apply the theorem with prime 2, we have S is 2 and Q is -7, which is 1 mod 8. You get all of them, it's fine. Well, this B greater than B at most 1 thing is because when the odd prime bit of our theorem 6.11 down here, in the odd prime part, you can only keep going if the power is even. And 28 is modulo 7, but not 7 squared. And then we don't even have to read this bit about whether or not the leftover section is 1 mod P. I assume we're going to see an example of that in a moment. That's very subtle. Here we are, fundamental discriminants class number 1. So theorem 6.8 tells us which numbers this form represents. Good. These are the numbers like this. Primes like this. That's Q2 represents exactly these numbers like that. And odd primes like this. Hence Q1 must represent at least these numbers with A equals 0, B at most 1. And odd primes like this. Since these numbers are all odd since A equals 0, but Q1 also represents some even numbers, since this could be even. From the topograph, we might conjecture, here we go, that Q1 represents exactly the numbers like this, with A not 1 or 2, and the same conditions on B. And the primes P, what? The same conditions on B and the primes P, and the same conditions on P and the primes PI as before. You can make these powers of 2. Not difficult to exclude 1 and 2. To see that Q1 represents all the predicted numbers, right, we're going to push on a little bit to see that Q1, which is x squared plus 7y squared, represents all the predicted numbers. For prime P, if a product like this is represented by a primitive form, then you can and you can put on 2 more factors of P if you like. That's always okay. Just by multiplying everything by P squared or something? No, maybe not. Applying primitive form, okay. Probably not. Case at hand with P equals 2, the form like this represents all the products like this as above. A greater than 1. So x squared plus 7y squared represents all these products with a greater than 3. Let's read the proof. There is a label P to the K, Q. K is greater than 0, and at least one of the regions adjacent to this region must have a label not divisible by P. Otherwise, oh my goodness, otherwise a vertex in the boundary of this region would have all 3 adjacent labels divisible by P. So the form would be p times another form, making it non-primitive. Thus the given form is equivalent to this, with c not divisible by p. I'm looking nearby, find me something that's not divisible by p nearby the form, and then b is something to do with the difference between those arithmetic progression rule. A form like this has discriminant p squared delta and is primitive, since its coefficients are not all divisible by p, nor are they divisible by any other prime, since such a prime would have to divide q, b and c, making it like that non-primitive, and then we're done apparently. Oh, and then you've now made this thing. The form has discriminant p squared delta and is primitive. Oh, right, you're allowed to make the discriminant p squared. Okay, I'm losing focus. I think I missed that the discriminant had changed in between. I think we're going to wrap up here. In the middle of reading some examples, but they are a bit involved, as we will see future stuff coming up. Can I get to the end of a section, or just stop in the middle of nowhere? I think I'm maybe stopping in the middle of nowhere, running out of steam. Well, here we are. Cubic forms. Ooh, cubic forms. Yeah, when are we going to do complex numbers, right? You've got all these real numbers. When are they going to be? When are they going to be like? When are you hyping up the sequel? Okay, I'm going to put the bookmark symbol in here. We're going to come back, I think, to read some more about non-fundamental discriminants like 40 and 28 and 12 and all these good numbers. I'll be back next week then. I think we'll call it there. Possibly Twitch will, well, we'll see, but possibly as a result of some adverts and some donations, we might possibly, might have a celebration. Well, who knows? Let's find out what that looks like. Values can x cubed plus xy squared plus z cubed takes. Who knows, right? I have no idea. Absolutely no clue. I love maths sometimes, but some of the knowledge that we have in maths is not quite as transferable as you might guess, right? We have so many terms and conditions, right, that I don't know how to transfer any of this to a different problem. Okay, right. I'm going to call it there, I think. Thanks for joining in chat. Thanks for people watching on YouTube as well. Sorry I was rude about YouTube earlier, but Twitch, what's it like? We're going to call it there, and in the words of Herb, I'm ending the live stream. Bye.